Hi, in this video we're going to be doing practice problems about delta G, which is Gibbs free energy. And our first question here, we're calculating delta G using delta H and delta S. So our formula is G equals H minus TS. So we're looking for G, and I'm going to do E as an example, alright? So for E, our H is negative 746.6 kilojoules minus temperature, which is, if it's not stated, assume temperature as 273 degrees Celsius. And, standard conditions, sorry. So it's 273 degrees Kelvin, 273 degrees Kelvin is temperature times delta S, which is negative 197.9 J per K. All right, now here, since this is J, we're going to be converting this to kilojoules, so 1000 joules per 1 kJ. So we'll be dividing this by 1000 kilojoules divided by 1000. So now we just use our calculator. Negative 746.6 minus 273 times negative 197.9 divided by 1000, and that will give us an answer of negative 693 kilojoules. And now 693 kilojoules per mole is our delta G, and negative 693, and since it's a negative, that means this is spontaneous. It's a thermodynamically favorable process since delta G is negative. Alright, and that's for example E. Now number 11, for a reaction that occurred at 197 degrees, the enthalpy is this and the Gibbs free energy is this, find delta S. Alright, so again, negative 46 is equal to 26.5 minus temperature was 197 plus 273, which is 470 degrees Kelvin times X, which is going to be our delta S. I'm going to use S this time. So S. So now first we subtract both sides with negative 26.5. So negative 46 minus 26.5, and then we divide both sides by 470, which is gonna get our S as 0.154 kilojoules. Since everything else is in kilojoules, now we need to convert S into joules. So when you multiply this by 1000, which we're gonna get 154 joules per mole, and that our delta S. So driving force of the reaction. So what is causing the reaction to be spontaneous or not? What is the main thing that's causing this reaction to be spontaneous or not spontaneous? And the way I remember it is H and S. So if it's positive, I'm going to draw a greater sign, and if it's negative, I'm going to draw a less than sign. And then first of all, delta H is positive, so I'm going to draw a greater than sign over here. And S is also positive, and we see it over here, 154. So this is also going to be this. Since both are pointing this direction, then the letter over here that is on this direction is delta S, which is entropy. Now, if delta H was negative, then this will be a less than sign. And if they're splitting both ways, then both delta H and delta S will be the driving force of reaction. And finally, if delta S was negative, then I'll be using a negative sign over here. And since both of these signs are pointing toward the H, then I know delta H, which is enthalpy, will be the driving force of the reaction. So this one is going to be entropy, because they're both pointing to the right. Now, if the temperature of the system decreased dramatically, will this system become non-spontaneous? So let's see over here. Delta H minus temperature times delta S. If this number suddenly turned very small, which when I say small, I just think of numbers like 1 or 2. All right, if this temperature turned into like 1 or 2 degrees Kelvin, would our process become non-thermodynamically favorable? And the answer is yes, because our delta H is positive and our driving force is entropy. So when this becomes too low, since this is calculating joules per mole and this one is calculating kilojoules per mole, when this becomes low to a certain point, this number will be smaller than this positive number. This number will be positive, and since this is also positive, multiplied by this negative makes this delta S, makes this whole thing negative. If this negative number is smaller than this positive number, then our delta G will be positive. And that occurs when our delta T is extremely small, and when we multiply by delta S, it will not be big enough to overcome the positive delta H. So in that case, yes. Now finally, at 375K, the decomposition of copper is not a thermodynamically favorable process. Now if solid carbon is added to the system, this reaction will occur. So let's see, in this reaction, O2 gets cancelled out, and our reaction would be decomposition of copper oxide, 2CuO2O, plus 2C in the presence of carbon, solid carbon, which makes 4Cus, actually I don't need to write that S, which makes 4Cu plus 2CO. And now to calculate if this is thermodynamically favorable at 370K, we just have to add the two together, since that's all we did. We just added the... So since we didn't do anything to the reaction itself, so we just simply added them together, we wouldn't do the same for delta G. So this is something like Hess's law when we learned earlier. So now that we added them together, one's going to be 280, one's negative 287, so the answer will be negative 7.6 kilojoules. And since the answer is negative, that means it will be TFP. And the main reason is because delta G is negative. And that's it for this video. Thank you for watching.